Welcome back to the Explainer. So, have you ever actually stopped for a second to marvel at just how incredibly fast your modern devices run? I mean, we literally demand our computers to process billions of operations per second, flawlessly, without even breaking a sweat. Today, we're unpacking the secret ingredient that makes all this magic possible. We're going to do a clear explainer video overview of Chapter 18 from our source material, diving deep into the fascinating world of instruction-level parallelism and superscalar processors. Basically, we're going to break down the architectural wizardry that turns a simple computer chip into a highly efficient, multi-lane superhighway of data. It's really cool stuff.
Okay, let's dive right into this. To make sense of this complex factory logic step by step, we've got a quick roadmap for us today. First, the need for speed. Second, superscalar versus superpipelined designs. Third, roadblocks, specifically dependencies. Fourth, the out-of-order solution. Fifth, register renaming magic. And finally, number 6, the big picture.
All right, kicking things off with Section 1, the need for speed, decoding parallelism.
So the core desire of pretty much all processor engineering boils down to one simple thing: doing more things at the exact same time, right? The faster we want to go, the more we have to overlap our work. And that brings us to a really foundational concept: instruction-level parallelism, or ILP. Think of a computer program like a massive list of chores. ILP is simply the degree to which those chores can be done at the exact same time without, completely messing up the final result. Like if I need to sweep the floor and you need to wash the windows, we can do those in parallel. Our source material makes it super clear that maximizing this parallelism is the absolute key to modern computing performance.
Moving on to Section 2, superscalar versus superpipelined, building a better assembly line.
Now you might be wondering, how do hardware engineers actually exploit all that parallelism? Well, they came up with 2 main architectural philosophies to build a better assembly line. And this brilliantly illustrates the leap from an ordinary scalar design to a superscalar design. If you check out the top organization, a traditional scalar setup has a single pipeline functional unit for integer operations and one for floating point operations. It's essentially one single assembly line. Now contrast that with the bottom. A superscalar organization literally duplicates these functional units. It's exactly like a factory manager deciding, hey, instead of pushing everything down one conveyor belt, we're going to install 3, 4, or even 5 separate conveyor belts right next to each other, running concurrently.
Now, what's really interesting here is how time factors into all this. Notice how the bottom axis charts time to contrast our different approaches. At the top, you've got a simple 4-stage pipeline handling one instruction per stage. Right below that in the middle, the superpipelined approach slices those stages up into even smaller, much faster chunks. But look at the bottom diagram, the superscalar approach. You can clearly see how 2 separate instructions are completely overlapping during their execution stage at the exact same base cycle. That's true parallel work.
So just to really cement this foundation before we move on, superpipelined architecture relies on temporal parallelism. It's one really fast, deeply divided assembly line churning through more instructions by just clocking them at a much higher frequency. Superscalar, on the flip side, relies on spatial parallelism, meaning genuine, multiple functional units, several separate assembly lines running all at once. And today, superscalar is definitely the standard method for building high-performance microprocessors. But, and this is a big but, adding all these extra assembly lines introduces some major drama.
Which brings us to Section 3, roadblocks, dependencies, and conflicts.
Okay, so processors want to go blindingly fast, obviously. But as they try to cram multiple instructions through these parallel pipelines, they slam into some massive traffic jams. Our source text outlines 5 fundamental limitations to parallelism. And yeah, I know these look like incredibly dry engineering terms: true data dependency, procedural dependency, resource conflicts, output dependency, and anti-dependency. But don't let the jargon intimidate you. We can actually view these simply as everyday physical constraints. They're literally just the digital equivalents of a worker waiting for a tool to free up or waiting for a specific part to arrive on the belt.
Let's make this super concrete. Think about a true data dependency, which is also known as a read after write, or raw dependency. It's exactly like our factory analogy here. You simply cannot paint the car before the chassis is actually built, right? It's impossible. If instruction B needs the mathematical result from instruction A, well, instruction B cannot start until instruction A is completely finished. It is a hard, physical limitation baked right into the program's logic.
And you can see just how devastating these traffic jams actually are if you guide your eyes through the shaded blocks here.
When an instruction hits a data dependency, or when two instructions end up fighting over the exact same piece of hardware, which is a resource conflict, the pipeline is completely forced to stall. Look at those blank, empty spaces on the timeline. That is wasted time. And in a superscalar processor that was specifically designed to do a million things at once, sitting idle is pretty much the ultimate sin.
So, how do we fix it? Section 4, the out-of-order solution, bypassing the traffic jam.
To get around these frustrating roadblocks, engineers had to come up with some incredibly clever, dynamic hardware fixes. We are essentially upgrading from a rigid, old-school factory to a smart, dynamic one. This out-of-order execution breaks the instruction lifecycle down into a simple 4-step process. First, instructions are fetched and decoded in their original proper order. But then, step 2, they get placed into this waiting area called an instruction window. And here is where the magic happens. In step 3, the processor actually looks ahead. If an instruction is stuck waiting for a part, the processor doesn't just throw its hands up and halt. It actively searches for a later instruction in the window that is ready to go, and it executes it immediately, totally out of order. Finally, in step 4, it takes all those chaotic results and neatly commits them back into the correct original order.
Which naturally leads us to Section 5, register renaming magic, solving storage conflicts.
Now here's the catch. That brilliant out-of-order execution creates a completely new nightmare of its own. Instructions suddenly fighting over the same temporary storage spaces, which we call registers. This causes two very specific conflicts, a WAO dependency, which is write after write, and a WAR dependency, or write after read. But here's the thing to remember. Unlike that true data dependency we talked about with the car chassis, these aren't actually sequence logic requirements. Nope, they're just storage conflicts. It's literally just two totally unrelated tasks accidentally being assigned to the exact same workbench. If an older instruction takes a really long time, a newer, faster instruction might accidentally overwrite its workbench before the old guy is even done. It's a mess.
So, the absolutely crucial point here is how we solve this mess, and the answer is register renaming. The hardware dynamically allocates brand new, hidden registers completely on the fly. Think of it like duplicating resources to avoid fights, giving workers their own temporary lockers so they don't bicker over the same one. If two out-of-order instructions both want to use register 3, the processor secretly just hands one of them a completely different hardware locker behind the scenes. This brilliantly eliminates the storage conflict without the original program ever even realizing it happened.
To put into perspective just how extreme this trick actually gets, check out this number. According to the source material, an Intel Core microarchitecture exposes only 16 architectural registers to the programmer. That's what the software sees. But behind the curtain? To make all this renaming magic happen and keep that out-of-order assembly line humming, it actually uses 128 physical registers. I mean, that's wild. It's massively duplicating physical resources just to completely wipe out those false dependencies.
All right, bringing it all home with Section 6, the big picture, putting it all together.
We've spent a lot of time looking at the microscopic details here. The pipelines, the out-of-order execution, the register renaming. Let's move to a wider view and see how this builds into an entire, beautiful machine operating in perfect harmony. Just look at this visual journey. Over on the left, you've got your static, linear program exactly as it was written by the programmer. The processor fetches these instructions, tries to predict the branches, and dispatches them right into that gray box, the window of execution. Inside this window, it is organized chaos. Instructions scatter, executing totally out of order based on true data dependencies and whatever resources are available. But finally, they converge on the right side, completely reordered and ready to be committed.
And that final convergence point is called committing, or sometimes retiring. This is without a doubt the ultimate magic trick of the Superscalar processor. Think about it. Because of all the parallel pipelines, the branch predictions, and that chaotic out-of-order execution, the actual mathematical results are being generated in a completely random sequence. But by holding those results in temporary storage and only making them permanent when the original sequential model says it's time, the processor makes all of this insane, mind-bending complexity completely invisible to the programmer. To the software running on your computer, it just looks like a simple, highly orderly machine that miraculously happens to run impossibly fast.
Which, leaves us with a pretty fascinating thought to ponder. As we continue to widen the issue window and add more and more parallel functional units and duplicate registers into the hundreds just to squeeze out every absolute last drop of instruction-level parallelism, how much further can we actually push these physical limits before we hit an absolute wall? We are constantly chasing this illusion of instantaneous execution. It's an incredible engineering feat. Anyway, thank you so much for joining me on this explainer of the Superscalar factory. Keep learning, keep questioning, and I will catch you in the next deep dive.